Wynn Jacobson-Galán. Sorry if I'm mispronouncing your last name. You can correct me. I believe you are a grad student at Berkeley working on extremely late-time light curve evolution and progenitor constraints of calcium-rich transients. So feel free to share your screen when you're ready.
Great, thank you. Yeah, thanks to everyone who organized this. I'm sorry we have to be online, but all the talks have been great so far. I'm really excited for the next couple of days. Okay. All right, this looks okay.
Yep, looks good. And I'll give you a 2-minute warning.
Sounds good. So yeah, I'm Wynn. I'm a third-year grad student working here with Rafael and Margutti at Berkeley. And one of my research paths is to work on calcium-rich transients. And a lot of that work has been utilized through space-based telescopes like HST. And my motivation for this talk was to kind of apply that to how we can expand the progenitor phase space of calcium-rich transients with Roman in the future, which I think is really exciting. Before I begin, I think it's important to make a land acknowledgement. I'm located on UC Berkeley campus. That is unceded territory. The work I did for these projects and these papers that I'm going to talk about was actually at Northwestern, but I think it's important to make these acknowledgements before we go forward with anything that we want to talk about. But that being said, I'll jump right in. The title of my talk has the words, or 2 hyphenated words, calcium rich. And I just want to give some background on that before I jump into specific transients that are quote unquote calcium rich. So what makes a supernova a calcium rich transient? So there's been some really extensive great work on this, compiling these samples, and these are low luminosity events. They're fast rising events, as you can see from this light curve here. They're typically hydrogenless, very strong helium, pretty normal supernova photospheric velocities. And the name really comes from the strength of their forbidden calcium lines. So they're really strong in calcium, they're calcium strong, potentially maybe not calcium rich so much, but either way, rich in emission, strong in calcium. That's where they get their name once they're out to an optically thin regime. And they're kind of found all over the place now, but originally and more recently, the sample has definitely pushed towards these older elliptical environments. Yeah, so with that in mind, I wanted to zoom in on one, prototypical nice case of a well-studied nearby calcium-rich transient, 2019 EHK, which I've worked on for a couple of years now. And it's just revealed a really, really amazing data set because it's one of the closest calcium-rich transients ever observed. It's an M100, and there's a lot of great things that happened with this transient. So I just kind of want to bullet point it before I talk about the 2 main sectors of this talk, which are pre-explosion and extremely late time, but there's some other fun parts about this supernova that make it so interesting. So it was discovered with this double peak light curve. The initial flux excess was probably due to shock cooling emission, or at least CSM interaction with some local circumstellar material. Related, we have evidence of that because we saw these narrow emission lines from shock ionized CSM. And we also saw for the first time this really luminous X-ray emission. So this transit really had a lot of things, and seeing X-ray emission was at least a first idea that these objects could have some sort of like CSM around them at the time of explosion. And the final thing I'll say is that because it was in M100, there's really this amazing archive of pre-explosion Hubble and Spitzer imaging of the explosion site before the supernova happened. So we were able to make some really nice constraints on the progenitor based on that data set. So moving towards that data set, what I'll highlight is the HST imaging because it's something that we can then use to look at the pre-explosion space. And so on the left, I'm showing an HST image of the supernova itself. And then the reference, this is an archival image almost 20 years before. And what we identified was that in this really large phase space of the SED, there was no detected source at the location of supernova 2019 EHK. And that made us conclude that the progenitor had to have been below this detection limit. And that, as we've heard from other talks, indicates a certain type of stellar system that could elude our data set and our imaging for such a long period of time across such a wide SED. So that was really cool because it was the first time we were able to do this analysis and reconstruct this kind of limiting or phase space of an HR diagram for a calcium-rich transient for the first time based on such a large availability of pre-explosion data and such depth too. So what I'm showing here is really a lot of ruled out regions for different extinctions. So the primary thing to look at is maybe like the light blue region, and then everything below that is permitted. And then everything above that is like ruled out based on the limit of our detections or non-detections. And for anyone that's familiar with these diagrams, you can kind of see that, you know, we're ruling out a massive chunk of the massive star phase space for calcium-rich transients. So we're really seeing that, you know, compact stars, low mass stars, binary stars are really the way to go if we're thinking about a massive star. And even the fringe cases, you know, it makes it hard to incorporate a massive star, even on the low mass side, as the potential progenitor for this specific calcium-rich transient, but it's definitely an option. But it really constrained it greatly. And obviously we can still make claims about white dwarf systems as the potential source of calcium-rich transients. But what will Roman do with things like this? So if we have additional objects that are observed in such nearby galaxies with pre-explosion imaging, we'll then able to make this, you know, parameter phase space for calcium-rich transient progenitors with additional objects that have pre-explosion imaging. And I think that if HST doesn't do it, then Roman will definitely do it. It will conclusively detect either a massive star progenitor for a calcium-rich transient, or if that does not happen, for enough cases, we can conclusively rule out massive stars as the progenitors, because I mean, just for 19HK, we almost pushed to the case where massive stars were, you know, not consistent with our observations. I think with even deeper observations, pre-explosion imaging and archival stuff that Roman will be able to provide, you know, this problem will be solved pretty soon. I hope. You know, it really takes a nearby supernova for this to happen. But moving on to much later phases, so that was before the supernova. Let's move further out in time when the supernova is much older. Still sticking with this case study, 2019 HK, we were able to get a couple HST programs approved, and we were able to observe this in multiband, multicolor imaging out to, you know, about 400 days after explosion. This is one highlighted epoch here where you can see the supernova is pretty old, but very cleanly detectable in its beautiful host galaxy. And so for the first time, we're able to construct this bolometric light curve sequence out to very, very late phases. So the red points, this is the supernova light curve, and the furthest points in time you can see extending out to almost 400 days are what we used HST for to build this complete bolometric light curve sequence out to late times. And this was not something that had been done for calcium-rich transients because they fade really quick. And we can't really extend out to when the power source is a lot more easy to pin down. And by power source, I'm really talking about radioactive decay, because that's the main agent that we think is pumping fuel and energy into the system at late times. And we should be able to test this kind of scenario if we're able to observe transients like this at late times. We do it for type 1As. It's been really great. So what we did was the similar method, but for a calcium-rich transient this time. And applying some model, we're able to fit these data really nicely with a simple pure radioactive decay power source, so no additional power source needed. But definitely, for those that are familiar, there needs to be some sort of escape of gamma rays and potential positron leakage as the ejecta is thermalized with energy. So that's very cool to make that test. Another thing you can actually do on the progenitor side is radioactive isotopes, especially cobalt-57 to cobalt-56, the mass ratio that you can infer can tell you about the progenitor density. It's linked directly in explosion models by very, very talented theorists who run these simulations, explode these models, calculate the nucleosynthesis, and then tell us, what are the ratios of these isotopes? What should you be seeing? And in black, I've plotted here for a range of ejecta masses. The stars are the range of upper limits on the total synthesized 56 cobalt to 57 cobalt to 56 cobalt. And that range is conclusively, only consistent with a certain type of progenitor, one of which was this merger of white dwarfs, compact low mass white dwarfs. And it doesn't really work as well with the nucleosynthesis that is predicted, or isn't predicted for massive stars. So I think this is a nice case, and I'll say that with Roman, we should be conclusively detecting and being able to model, radioactive decay products like cobalt-57 and really detecting them as power sources, because if we go further and further out to late times, we should be able to see this power source in much greater detail. So what does the future hold? What have I kind of rambled about for the past 10 minutes? So we have really nice examples of calcium-rich transients in nearby galaxies that we've been able to use pre-explosion and extremely late-time imaging to understand their progenitors, which are unknown currently, but we're really getting to a point where we can start to constrain them. And pre-explosion imaging will increase the amount of, increase our knowledge of what is the parameter space of progenitors that could potentially produce calcium-rich transients, either by non-detection or concrete detection of a potential massive star, or non-detection of some sort of compact system like white dwarfs. And extending that into late time, space-based telescopes, especially Roman, will be able to follow these objects and more of these objects out to very, very late phases, hundreds of days, where we normally would never have been able to detect them anymore, and to constrain the nucleosynthesis that's produced in the explosion, specifically iron group elements, cobalt-56, cobalt-57, iron-55, these things that we haven't been able to constrain in terms of mass products in these thermonuclear transients before. So it's really exciting. And I think the future is really bright for Roman with these objects, and we just have to find more. So with that, I'll take some questions, and thank you for having me.
All right, thank you very much, Wynn, right on time. All right, we have a few minutes for questions. I don't see anything posted. I will give everyone a second. A little awkward silence to stimulate a little thought.
All good.
I have a question for you if nobody comes in, but I'll give everyone about 10 seconds. Every time a moderator says, okay, no questions, I was like, oh, I was just about to ask one, actually. Okay, well, I'll ask mine, and you can, somebody else can fill in if they think of one. So going back to the detection of progenitors, I haven't actually worked out the numbers yet, but do you have an idea, calcium-rich transients aside, maybe what, generally, like what sort of, stellar mass star you could, detect out to a given distance? So like, 10 solar mass star out to, 5 megaparsecs, 20 solar mass star out to 10 megaparsecs, something like that. Have you worked out any of those numbers yet?
For Roman specifically?
Yeah.
I have not. I just briefly looking at the numbers for calcium-rich transients in just 2019 HK in particular, it seemed a lot more promising that we could detect for that a similar object at a similar time, like distance scale. You could definitely detect, much lower than 8 solar masses for
Right.
16 megaparsecs is what 19 HK was at. So I guess that was my starting thought.
Yeah, I'm just wondering, that's great. Yeah, I'm just wondering what the implication is on other supernova types. So I don't know if anyone's worked that out. Maybe we can talk about that. at
I
another
mean,
breakout.
yeah, it's always fun to talk about it with the progenitor problem in type 1As. Will we see like some sort of main sequence companion, or
Right.
will we be able to place like really great limits better than even HST for like 11FE and stuff?
Exactly.
Yeah. So I mean, calcium-rich transients fall in that same realm. It just only took one nearby one to actually get some sort of questions answered, and then more questions left open.
Yep. All right. I think we can wrap it up there. We're a minute over time.
Cool.
Any last questions? I'll give you one more chance while the next speaker sets up.